Okay, now let's look at coaxial Covet flow, and the setting is pretty much two cylinders with the same center, and one is the inner tube is stationary, the outer tube is rotating with omega naught, and the inner radius is Ri, the outer radius is Ro. I stands for inner, O stands for outer. And here's a summary of the way to solve such problem. You pretty much look at the symmetry. This is have obvious symmetry in terms of phi, the rotational symmetry in terms of phi, and also the translational symmetry across z. So obviously dd phi is 0, ddz is 0, and vz is 0. And based on incompressibility, with some manipulation, we'll get Vr equal to 0. And from Navi's Stoke equation, we'll have V phi in such form. Since Vz and Vr is 0, then V should be equal to V phi. And apply two boundary condition in the outer and inner layer. Basically, it's a non-slip boundary condition. In the inner layer is 0, outer layer is the velocity of the surface of the outer tube. And after all that calculation, we're left with the final solution of V equals this. You can find some my note in the description, and you can access another video from institute from India. It's very good. And so let's look at the details. In the cylindrical coordinate r is phi z, we have the obvious symmetry that we discussed. So it doesn't make sense to go up and down, because if you have velocity anywhere, then they have a preferred direction, and that violates the translational symmetry. And similarly, you should not have any preferred location have a higher velocity in phi, so phi should be a constant across r or across phi. So with dd phi and dd0 will be 0, and ddr should be 0 as well. Vr is non-zero because of the incompressibility that we're going to apply here. Using the divergence definition, you can find on online the divergence for cylindrical coordinate. You'll find dd phi is 0 from the symmetry argument, ddz is 0, so we're left with this function with only r. So we're left with such solution based on the boundary condition of non-penetration solution. We know that the fluid won't flow into the tube or out of the tube when it's on the boundary. Then this has to be true for r equals ri or r equals r naught. So the only way to satisfy both boundary condition is Vr naught equals to 0. Thus, Vr equal to 0. And let's look at the Navi-Stoke equation. And here's the full equation. For us, we're only curious, and it's only useful to look at the phi direction, because r and z direction are relatively trivial, and it should be self-consistent with a previous derivation of Vr and Vz equal to 0. And then we look at this. Look at the definition of divergence. Look at the definition of Laplacian in the cylindrical coordinate, and we look at the phi direction, left with those terms. We know that we're looking at steady state, so ddt equal to 0, and it's phi independent. So any derivative of phi will become 0. And this is also phi independent or Vr equals 0. So we're left with this two terms. So we have that. We can reverse we can use the Laplacian in the cylindrical coordinate to expand it with such definition, and left with this expression. We know that is phi and z independent, so we're left with those two terms. Use this substitution. You can check it's definitely true, and then we're left with a second order partial differential equation with very obvious solutions, A, R, N. You can guess this and plug it in, and you'll find that the final solution will be we plug in this, so we solve for n. Then we know that n equals plus minus 1. Then we have one term is r, another term is 1 over r. Then we're left with this expression. Basically plug this into here. If you learn ordinary differential equation, you will see why that's the case. You can skip ahead, but I will tell you basically, if you see that second order derivative, first order derivative, and no derivative, it has 1 over r squared, then it's pretty much the signature of the solution of ARN as a solution, because for the polynomial you have, then it will make the order of n even with this differential equation. And we'll apply the boundary condition of phi, non-slip boundary condition. In the inner layer is 0 because stationary. We have this. Outer layer is 0. We have those two equations. R equals R out equal. Yes. Since those, based on those two, this one equation. Why it keep giving me? Yeah, so this boundary condition give us both. We solve basically two unknowns, A and B, and two equations is solvable. So we solve for A and B, plug back into this expression, we end up have the final answer. And in summary, look back into it, we look at the symmetry, reduce the degrees of freedom, and use the incompressibility, the assumption, to get one more thing, and use the Navi-Stoke equation, solve for the differential equation, get the solution, apply boundary condition to arrive to the final answer. Just like the recipes that I discussed in the previous video.